Universität Hamburg, and the title is Quantum Coherence and Quantum Entanglement in Photosynthetic Light Harvesting Complexes.
Okay, thanks for the introduction. So, back to coherence and photosynthesis. Craig actually introduced most of it this morning, so I'm not going to repeat it. Just to remind you, these are really the first 4 steps of photosynthesis, and all the rest of it we are not concerned with. So, the main 2 puzzles I'm concerned with here now is, first of all, an old puzzle, which is that the transversion exciton, which is formed after the absorption of light to the reaction center, is very fast. It goes in time scale of picoseconds, so about 50 picoseconds maybe. But the decay of such an exciton and the emission of a photon again, that takes a nanosecond. So on these timescales show you already this transport is almost perfect. That's an old puzzle. Now, the new puzzle, which Craig told us about, is that now it was found that the transfer process in various systems shows quantum coherent behavior. So there are now lots of experiments around showing this in various systems, and this raises directly the question, is there some connection here? So the first natural question is this quantum coherence maybe responsible for this high yield in this transfer process? Or if you make it a little bit more open, you could ask, does quantum mechanics really serve a purpose in photosynthesis? Or in the other end of the scale, is it just pure coincidental result of energy and length scales here? So there are lots of work trying to tackle both of these questions right now. My personal opinion is, so far we certainly have no final answer to these questions yet. So, but that's not what I'm mainly concerned with. So, I'm not trying to figure out why do we have this coherence? Why does it survive? We have a biological system, this has something to do with life, we are at room temperature. So let's look at the scales. The biggest electronic couplings you usually find is this 100 inverse centimeter. It's the biggest one they have in the FMO complex we heard about. If you translate that into temperature, that's 150 Kelvin. So in that respect, we at first have to realize room temperature is not really high for these systems. So why do we usually argue we shouldn't expect it? Well, if we think about how we destroy coherence, it's by environmental fluctuations. And what is fairly well established from experiments is that the environmental fluctuations in these biological systems are typically coupled to our quantum systems rather strongly. So if we have a strong coupling constant and we put that in just a golden rule expression, 1 phonon rate, what you get is overdamped dynamics, so you should expect classical hopping transport. Now again, that's not what's found. So how does it work? So we try to tackle this question now really by using the simplest model approach we can think of. So we are certainly not answering with that any details of an FMO complex or an even more complicated system, but we are trying to answer in a simple model system, how does it work that we see coherence, or how would we expect it to be destroyed? So we take a donor-acceptor system, we have the 2 chromophores, donor acceptor, an excited state, there's an electronic coupling between them, and we go even a step further, we say we really only focus on the situation where we have a single exciton in the system, so we really just end up with this Hamiltonian, so both energies are even equal. That's the quantum Hamiltonian for our donor acceptor system. Then we just couple harmonic oscillations to each of these 2 chromophores. Now, we're interested in the dynamics in the system, so what we need from the environmental fluctuations is basically their spectral function. And so, the standard approach, which is around, I think, is to couple totally independent fluctuations to each of the 2 chromophores. So, but in this first paper by Lee in 2007, they speculated that we have spatial correlations, solving the problem of answering how we get these long coherence times. So we said, well, let's take that into account. Let's allow for spatial correlations between the fluctuations coupling to this chromophore and to this chromophore. Now, if you want to really make such a model, you have to answer one question first. If you're coming from condensed matter, you are usually thinking in a bulk. You have normal modes, so you have propagating phonons. So if you do such a kind of model, then you end up with something like that. So your spectral function has a coupling constant alpha. We use an ohmic spectrum, so it's linear in omega. It has a cutoff function with a cutoff frequency omega c. And this is the term which actually gives you the spatial correlations between the two chromophores. And what's entering here is the distance between the two chromophores over the speed of sound. So this is now a condensed matter viewpoint. If you now go into the chemical physics stuff, you always argue about vibrations of proteins. That's a rather localized thing. So you would make a model with localized modes. So still the first part is the same, coupling constant, linear and omega, cutoff function was a cutoff. But then you argue, okay, we have an exponentially decaying extension of our modes, and now the dependence is on the distance over some kind of localization length for these modes. Okay, that's a problem. That's what we now have to solve, and we have now to realize one more thing. If you look in the literature, for all these parameters, what you'll usually find is you get values for alpha and omega c, so alpha is rather strong. However, omega c usually is rather small, so it is on the order of these electronic couplings. That is, for the way you try to solve this problem, rather important. It does not allow you anymore to do any of the analytical approximations typically. Okay, and I should say one more thing. There's little knowledge about these spatial correlations around. So we have no values we can use here. Okay, just very short on the method. As I just said, analytical approaches usually fail in that parameter range, so we use a numerical approach, the quasi-adiabatic path-integral formalism. It's heavy numerics, however, it allows us really to exactly solve the problem. So we don't have to discuss in the end if the approximation does anything, there's simply none in it. Okay, and with that, let's go to results. So what we did, we put an exciton to the donor, and we plotted here the population difference between donor and acceptor over time for different cutoff frequencies omega c. And what we typically find, that's nothing else what we would have expected, is coherent oscillations. But the interesting part here, it's difficult to see, but for large omega c's, the decay of these coherent oscillations is rather fast, whereas if you go down where the omega c equals delta, then you have long-lived coherence. So if you want to have a different viewpoint on what small omega c means, a small omega c actually means that you have temporal correlations between the fluctuations at a single chromosome. So what it shows you, okay, we can generate long-lived coherence if we just have a small omega c. As actually experiments would tell us that this is the case right now. However, we also look now at spatial correlations, so this time now we fix the omega c to be equal to delta. If we now discuss spatial correlations, we need to discuss the distance. We've chosen these 3.8 angstrom, it's the distance of the chromophore 1 and 2 in the FMO. And this electronic coupling is the electronic coupling of these two, so to be close to the FMO system. And okay, now it's actually plotted the population of the donor. Time is running to the front this time. And here we plotted now the speed of sound. So as a small speed of sound, you see a fast decay. that describes non-correlated fluctuations, so the spatial correlations for small speed of sounds are very weak. And if you increase the speed of sound, you increase the spatial correlations, and then you see that the coherence times gets longer and longer. This is nothing really so unexpected, since if you have full spatial correlation, that means you move your levels just in the same way. So then these fluctuations don't disturb the dynamics at all anymore. However, what's maybe interesting to say here is that if you look at scales, water has a speed of sound of 1500. So that would be around here. So, well, ice has 3500. So that's about here. So it seems to be in the range we should discuss. Now, this was for the model of propagating modes. We can do the same with the localized modes. You see the same. So the localization length now varies from 0 to 1.5 nanometers. So the FMO, I think in general the size is something of 20 nanometers. So these are not unreasonable sizes. And you again see for no spatial correlations, the decay is rather fast, and the decay gets slower and slower if you increase spatial correlations. So, in general, all I'm trying to tell you is long-lived coherence, so 1 picosecond, similar to what's found in experiments, if you plug in all the parameters, is not so surprising if you allow for these temporal correlations and or spatial correlations in your environmental fluctuations. Okay, that is as much, at least that's what I believe, that is as much as you can do with a simple two-level model, a donor-acceptor system. Now, once you believe that it's not surprising anymore that we see this coherence, then you should do the next step. You should ask, does it serve any purpose? And from our starting point, since we're always starting from simple models, we extended our very simple model to the next more complicated one. So we looked at 2 donor-acceptor pairs, we've chosen them identical, and we wanted to know what the spatial correlations really do here. So both systems are really identical, so the distance between the donors and the acceptors is identical, but we have now an additional distance between these 2 pairs. So if we think of them in terms of channel, where we put excitonic energy through, we can have a case of distant channels and a case of very close channels. So let's look first at the distant channels. Then, without going into the details, basically these are the same again. So for a small speed of sound where your spatial correlations are weak, you see a faster decay than for strong spatial correlations. However, if you put your channels very close to each other, you actually see the opposite. So, in this case now, with small spatial correlations, the coherence lives longer than with large spatial correlations. I should add one more thing, just to confuse you a little more. These 2 pictures were now a rather low temperature. If I go to temperature of 150 Kelvin again, then this will stay the same. I mean, everything decays a little faster, but the general feature stays. More spatial correlations, longer coherence. This will not survive. So, from this, we concluded, well, spatial correlations can do basically everything. They can enhance decoherence, they can suppress decoherence. It all depends on the various parameters involved. So with this, I really tried to tell the experimentalists we need to know how big are these spatial correlations and how do they really work. Then we can put them in our models and see how big their effect really is. Okay, one more step. Since many people discuss that the coherence by quantum speedup for search algorithms does this superior quantum yield. So we said, well, for that you usually need entanglement. So let's look at entanglement. And we used the negativity as an entanglement measure. And again, we just plotted over time this negativity, which is color-coded. And on this axis again, we varied our omega c. So basically the temporal correlations in our fluctuations. And in the main picture, we introduced also a direct dipole-dipole coupling between our two channels, whereas in the small inset we had no direct coupling. I should say, these are closed channels, so they are so close that we have spatial correlations in our fluctuations as well. And what we see is, for large omega c, nothing really happens. But if you decrease omega c to where it's believed it should be in this biomolecular stuff, you see the emergence of entanglement and then a decay, and the lower you go, the more oscillations you find. So we are basically starting out of an unentangled state, that's what I should say. So the time scale of these oscillations goes with this coupling, as one would expect actually. However, now look at the inset. So even if you don't have a direct coupling, you still have the emergence of entanglement for these small omega c cases. And this is a result of the spatial correlations which actually introduce a direct coupling between these two channels. So closed channels are really communicating if you have spatial correlations. The same holds for larger couplings, and it's not showed. This again was a low temperature. You can also do it at the higher temperatures. It stays more or less the same. So from this you cannot say biology uses entanglement. All you can say is these slow bus systems, so small omega c, they support really the emergence and the death of entanglement. And if you add to it spatial correlations, then you can generate this entanglement even in channels which do not have a direct coupling. So this is a strong hint that there is a big chance that entanglement is present. Now someone has to prove that it's relevant. Okay, and with this I thank you, all the ones who do this work with me, and the financial support of the Freiburg Institute for Advanced Studies, where all of this work was actually done.
Thank you very much, Peter, for the questions.
Shouldn't one understand these oscillations in the limit of small omega c as a vibrational coherence and quantum coherence? Because in the, for instance, in adiabatic electron transfer theory, this is well known. I mean, this is a completely classical case, and you still have oscillations.
No.
So I mean, I just object to the word quantum in interpretation of this type of oscillation. I would say this is a fully classical phenomenon because you have a slow path.
It's not a single mode. What you in principle see is this is really the oscillation of the quantum system. But the problem is when you decrease your spectrum, so you decrease omega c, then you have no resonant modes anymore. So you suppress strongly the one phonon process. This is the main thing. So you don't have any decoherence. So what you actually see here as decohering effect is multi-phonon processes. But it's not a coupling between the vibrational mode and the actual quantum system.
And if I may comment, omega c is not much smaller than delta. It's comparable. This is
So
a
you say
transition
if
shift.
it goes to zero, this is again a different story.
Yeah, this we don't know. We cannot also calculate. Right?
So it seems that there are two pieces of data to be fit simultaneously, and I understand how the spatial model does it. I have a question about this omega c. That if our splitting is about 100 wave numbers and omega c is about 100 wave numbers, but our ground excited coherence is 12,000, what do you predict for the dephasing of the single quantum coherence in this model? Much, much faster than this?
We haven't actually done that.
Well, but I mean, it seems to me like that you would predict that now omega C is extremely small compared to the splitting. 12,000 versus 100, you would say that those would persist
Yes.
for an extremely long time, which is exactly the opposite of what we see in the data. I mean, I think that's another way of phrasing what you were saying with the vibrational model. That vibrational coherences last for a very long time, but we have to make sure our picture is consistent, that we're watching the same states all the time.
Yeah. However, the values for alpha and omega C are actually taking from the papers, analyzing these linear absorption things. So it should fit. I mean, they fit their data, get out these values, and I'm using them. So I haven't repeated the analysis.
Just have a simple technical question. When you have the ohmic spectral density, right?
Yeah.
So normally, in order to keep the whole system bus coupling constant, when you change your omega C, you have also to change your coupling constant. You call it alpha, I think. Because what actually happens when you have an ohmic spectral density, just imagine it, then you choose, say, change your omega C to smaller values. Then you just have less overall coupling, because to keep the coupling constant, you have to keep the integral of your spectral function of all frequencies constant.
That is when you use as your coupling strength the lambda, so reionization energy. It's just, I agree with you,
Yeah.
if you want to keep the reionization energy constant, then if you make omega C smaller, you have to increase alpha.
Yes.
That is true. I'm not doing that.
But then in a certain sense, what you see when you decrease omega C, you decrease the system bus coupling strength, and then your oscillations survive longer.
Yeah.
Which is kind of trivial. I'm sorry.
Well,
at least in my idiotic point of view. I mean, the less coupling I have, the longer the oscillations.
Well,
this is basically what it is. But when you say this is trivial, then no one should have ever said anything about wondering that we find coherence. Then it's really clear. Then the experiments give you alpha, they give you omega C.
I love coherences, and I love that it survives so long. Yeah, it's really great. But I just mean that when you're exploring the dependence on your omega C, your argument is that it depends how fast or how slow your bars is. Yeah. What I'm saying is that if you don't change your alpha parameter, then when you decrease the omega C, you just decrease the overall system bus coupling strength. And this makes the whole thing to survive longer.
That is perfectly right.
So, okay.
But I think you would similar, you would find.
If you keep the reionization energy constant and you do this game, what you then basically do is you are playing around with the model. Then
We're all playing this somehow else.
But it's a different playing around. If you make omega C smaller,
Yeah.
you usually suppress the one phonon process. If I keep alpha constant, then that's all you see, and that's what you say. You suppress decoherence and you suppress the spectrum. If at the same time I increase alpha, all I do is I increase at the same time my multiphonon processes. So it doesn't give you a new information, and what's in the end important is what is the reionization energy from the experimental point of view, right?
Right. And, well, this is unnecessary. I'm just saying one simple thing. Yeah, just if you think in a very simple way that you have a coherence and you have a certain decay rate of this coherence. Yeah. If you do a number of approximation to any system bus theory, at a certain point you just come to a certain rate for your coherence to decay. Yeah. And if your system bus coupling is weaker, then your rate is just like it is a slower process because your rate is smaller. That's all I'm saying.
But the question is what's strong and weak coupled. You say it's a
But we can
reionization
continue
energy.
afterwards.
if you go into the literature of the condensed matter, it's really alpha, what people discuss. But it's basically looking in slightly different ways on the same problem.
We can plot our data in a different way. I think we would find the same. We have changed also omega z and alpha, so we have the data, so we can check.
Yeah, I believe you. I'm just well, okay. Maybe I just can't express my point.
There is a question here.
So define spatial correlation on a local basis set. And I think if we define a spatial correlation on a S-term basis set, then it will always enhance coherence.
Could you repeat that?
Now, you define the spatial correlation based on a local site basis set.
Right.
But if you define the spatial correlation based on an S-term basis set, then it should always enhance coherence.
So we can check. We haven't done that calculation. More question? Yes, please.
Well, what happens if you add this order to this model?
That's a very good question. If I do it in a donor-acceptor system, I'm not changing anything. I mean, all the graphs look a little different, and everything gets a little bit more complicated, but all final conclusions would stay the same. It's going to be different if I go to more complicated models. So this double donor-acceptor system, we haven't done that yet, but something new might emerge, yeah.
Because we always thought that if you had this effect, you have also an experiment, an old experiment, that was analyzed by Vladimir, where we thought we saw quantum coherence with two, let's say, localized states, but no oscillations. And we said, yeah, the reason is that we have so many frequencies at the same time that in the end it ends up like a sort of quasi-exponential decay. So I was wondering if you would do the same thing. If you really assume a reasonable amount of disorder, that you will also kill this oscillatory nerve.
We could do that, yeah, but we haven't done that yet.
Yeah, but what would you think?
Yeah.
Well, this was a meeting where people should think.
If you introduce disorder, which basically means you just integrate over your parameter set over a certain distribution in the end, then you will erase most of the coherent things you see.
And I have another question which is associated with this. I have really very, very big problem with this idea, and I also expressed it to Greg, who argued with me. This idea to couple only to one single local mode in the system, one local spatial mode. Because these systems are really complex. They have, if you look at their frequency spectrum, there are a zillion frequencies. And all of them are, most of them are weakly coupled to the optical transition. Or many of them, let's say it this way. So I have a hard time, so I would think that all of them sort of contribute a little bit. And then again you would kill this whole picture.
This is
So it's a bit close to what the lady in front of was saying.
So what this model actually does, it's not coupling a single mode, it's coupling a spectrum. However, it's a continuous spectrum. So if you think on that, you have a certain part, a continuous spectrum, then you have certain strong lines in the spectrum as well.
Many.
Yeah, so...
You're all excited.
Right. And I have to say, single lines would make something different. It's not included in the model. This is really what a continuous spectrum of environmental modes do. If you have on top of that single lines which do not overlap, so you really can say this is 1,000 centimeters, inverse centimeters line with a certain width, that would to be needed. Then we would need to include that exactly into these equations, then something else would come out. And that also means that with this approach, something like a vibrational coherence cannot be treated. Then you really need to put in a vibrational mode specifically. And we only do a continuous spectrum.
Yeah, last question.
This is sort of comment on Rink's question a little bit. I mean, it's not just how well they couple to the optical spectrum. There's a broad range of modes that would do that, but they have to couple to causing differences in the site energy, which means that they have to be they have to, in a sense, distort different molecules in different ways as the environmental mode to cause these fluctuations. So I think it's a much smaller part of the spectrum of spatial fluctuations that are coupled to destroying the sort of coherence between two chromophores than is coupled to destroying the coherence between the ground state and the excited state. Right?
Yeah, but there would still be a lot of modes.
There's a lot of modes, but the coupling strength to those is likely to be much smaller, right? Because they...
Yeah, but I mean, my argument would be maybe there's one strong couple, but there are about 10 million which are weakly coupled. And then it's simply entropy arcane.
I don't know.
I mean, 10 million will always beat the one.
If it were really a single mode coupling type of system, you wouldn't be able to explain either the temperature dependence or the isotopic substitutions. It could, now whether it's David's small but still large number or your really large number, I can't say, but if it were countable, 10, 1, 3, you would not be able to explain either the temperature dependence because they're somewhat enharmonic.
So it has to be large.
It has to be pretty big. I can't say if it's David's subset, but large subset, or your, all of them. I don't know, but it's not 3, it's not 10. It's a lot. It might be 100,000, it might be a million, it might be 10 million, but it's thousands would be reasonable. Otherwise, if you do this 30% deuteration, you would expect to see rapid dephasing in the ensemble. So you have to have some group of modes being substituted for some other group in that picture.
When do you expect deuteration to have any effect at all? I mean, most of the modes involved here are going to involve relatively heavy things where deuteration is a small perturbation to the masses.
It's there's at 300 wave numbers. I mean, you are talking about carbons, but you're changing the mass of this system. You're changing the direction of these normal modes. You're not going to change the spectral density in that region much, but if you're talking about specific motions, I think they will change. I think you'll see the normal modes change enough that you would see this. Carbon-13 is another. We don't see it slow down at all with a 97% carbon-13 substitution.
I mean, you deuterate solvents like methanol, it makes no difference, right? I mean, to their solvation dynamics, basically. I would argue it's the same thing that would happen in these proteins.
Okay, so we have to move on in the program to the last talk.